Okay, imagine this. What if you could jump into the quantum realm, like Ant-Man, and then just for a moment, hit rewind, but only for one specific particle? Could doing that let you measure something totally hidden, something scrambled away?
That's actually surprisingly close to the heart of what we're diving into today. It touches on some of the deepest questions in quantum computation right now.
Right. So our mission today is to unpack a really dense but potentially game-changing paper. It's from Google Quantum AI and collaborators, just published in Nature. They seem to have found a way to use this kind of quantum time reversal idea.
Exactly. To probe dynamics so complex that even the world's biggest supercomputers can't keep up. They're talking about a path towards practical quantum advantage.
And for you listening, especially if you want to get a handle on how quantum mechanics deals with, well, chaos without getting lost in the weeds, this is for you.
Yeah, we'll try to cut through the jargon. Let's start with a basic problem. Quantum systems, especially big ones, tend towards messiness. When you have lots of interacting quantum bits or qubits, any information you start with just spreads out incredibly fast, gets all mixed up. We call that scrambling.
Scrambling. So, like, if I put a drop of red dye in a swimming pool, initially it's localized, but super quickly it's just everywhere and nowhere.
That's a great analogy, and the system becomes ergodic. Fancy word, but it just means it forgets where it started almost instantly. It loses memory of its initial state.
Okay, so if you try to measure it using standard methods,
Yeah.
what do they call them? TOCs.
Right, time-ordered correlators. Those standard measurements just fade away exponentially fast. In their experiment, after maybe 9 cycles, poof, useless. The information is gone, completely scrambled.
Chaos wins, basically. So the big question is, how do you get that information back once it's been, well, put through the quantum blender?
You kind of force the system to undo what it just did. The trick they use involves refocusing or echo sequences. Think of it like this. You let the system evolve forward for a bit, then you apply a specific set of operations that effectively runs the evolution backward for the same amount of time.
Ah, like playing a tape forward, hitting rewind precisely, and then playing forward again.
Exactly. And if everything is perfect, the original state should reappear. It echoes back. But the real magic happens when you look at the imperfections, the interference patterns created during this process.
Interference.
Okay.
And that's where these other things come in. OTOCs.
Yes, out-of-time-order correlators,
Yeah.
OTOCs. They are designed specifically to measure the effect of this kind of forward-backward evolution. They capture the interference between all the different possible paths the quantum information could have taken.
So unlike the standard TOCs that decay super fast.
OTOCs decay much slower. Algebraically, not exponentially. It's like the difference between falling off a cliff versus rolling down a long hill. It pushes that point where the information becomes useless much further out in time.
Okay, so these OTOCs, the first kind, let's call it OTOC1 or C2 as they do in the paper, they already help a lot, right? You said they maintain sensitivity past 20 cycles.
They do, yeah, which is already a big improvement.
So why go through the presumably much harder effort of measuring the next level up, this higher order one they call OTOC2 or CT2? What was the big deal there?
That is the million-dollar question. And it's because CC sees something fundamentally different. It's way harder to measure, yes, but the payoff is potentially huge. Think of it like this. CT2 might sense the local ripples caused by the chaos, but C2 can detect the massive underlying tidal wave.
Ripples versus the tidal wave.
Oh.
Okay, I like that. Let's unpack that. What causes the tidal wave?
It comes down to how information actually spreads in these systems. It propagates via something called polystrings.
Polystrings, like little paths the information takes across the qubits.
Sort of, yeah. They represent fundamental ways entanglement spreads. And as these strings evolve, the paths they trace out in the abstract space of all possible quantum states, well, these paths can form loops.
Loops?
Like circuits.
Kind of. Interference loops. Now, the standard OTOC, it mainly picks up interference from small loops. These are loops that basically enclose zero area in that abstract space. They tell you about nearby interactions, local stuff.
Okay, local dynamics. Makes sense.
But the big breakthrough, the reason I went for seedless self is that it's sensitive to constructive interference from polystrings forming large loops.
Large loops. So these paths are stretching much further across the system, maybe involving interactions between distant qubits.
Exactly. These loops can enclose huge areas in that configuration space. They represent really complex global correlations. And here's the kicker. This large loop interference mechanism is essentially invisible to C2 or any lower order measurement.
Wow. So CETA has like a special lens that can see these hidden large-scale patterns that the other tools miss completely. Precisely. It's like going from, I don't know, a magnifying glass to the James Webb Space Telescope for looking at quantum chaos. It reveals a whole new layer of complexity.
Okay, but how did they know this large loop interference was really the reason C was different? Could it have been something else?
Good question. They tested it. They deliberately messed with the system during the evolution by inserting random operations, random Pauli operators. The idea was that these random operations should scramble the phases, the signs associated with those large complex loops. It's like shaking an interferometer.
And what happened?
Changed dramatically. Its value dropped significantly, showing it was highly sensitive to that randomization of the large loop phases.
But the simpler one, CT dollars.
Its C2 barely flinched. It wasn't really affected, which confirmed that its sensitivity comes from different smaller scale effects. It proved the large loop mechanism dominates CT dollars.
Okay, this is really cool, but it also sounds incredibly complex. Which brings us to the so what question. If CREN captures all this complexity from large loops, does that make it hard for classical computers to simulate?
Bingo! That's the crucial link. The very thing that makes CC sensitive, that large loop interference, is also what makes it a nightmare for classical simulation algorithms. It creates what's called a severe sign problem, making it incredibly difficult for classical methods, especially those based on sampling, to get an accurate answer.
So, is this it? Is this genuine beyond classical territory? We hear that phrase thrown around a lot.
Well, here they provide some pretty compelling numbers. They argue, yes, for this specific task, they've crossed that threshold.
Okay, lay it on us. What did the quantum processor achieve?
They managed to measure a specific part of CC Ward, the off-diagonal component, which captures the crucial interaction information on a system with 65 qubits.
65 qubits. That's a decent size. How long did it take their quantum computer?
Get this, about 2.1 hours per circuit run to collect the data with good enough accuracy.
2 hours. Okay, seems reasonable for a complex experiment. Now the comparison. How long would it take a classical supercomputer?
They estimated the time needed for the Frontier supercomputer, one of the fastest machines on the planet right now, to simulate the exact same thing, to the same accuracy. Using the best-known classical method for this, something called tensor network contraction, which is essentially a brute force mathematical approach.
Okay, and the time. Don't keep us in suspense.
The estimate converged to approximately 3.2 years.
Wait, seriously, 3.2 years?
Yeah.
Compared to 2 hours?
Years! That's a speed-up factor of what, roughly 13,000? It's pretty stark.
Wow. Okay, that's not just incremental. That feels like a genuine leap.
Yeah.
For this specific hard problem, the quantum approach is just vastly faster. That really puts beyond classical into perspective.
It does. And they also showed that other classical approximation methods, like one called cached Monte Carlo, just couldn't reach the accuracy the quantum experiment did. The signal-to-noise ratio was much better on the quantum device.
So this isn't just some theoretical curiosity. It has practical implications, right? This OTOC2 thing.
Exactly. This leads straight into the idea of practical quantum advantage. They argue C dollar hits a kind of Goldilocks zone. 1, it's measurable accurately enough on current quantum hardware. 2, simulating it is demonstrably beyond classical reach. And 3, crucially, it provides practically relevant information.
Okay, criterion 3, what kind of relevant information? What can you do with this C dollar measurement?
They demonstrated a proof of principle application called Hamiltonian learning.
Hamiltonian learning. Sounds like learning the rules of the quantum game.
Pretty much. Think of it like quantum forensics. You have a quantum system maybe representing a new material or molecule, but you don't know the exact physics governing it, the Hamiltonian. You want to figure out its parameters.
Do you use the quantum computer?
Right. You measure C by Lar as your actual physical system, or a quantum simulation of it. Then you create a model of that system on your quantum computer, but with some unknown parameters, maybe the strength of certain interactions, represented by a phase famine in their example.
And you compare the measurement from the real system to the simulation.
Exactly.
Okay.
You calculate CC dollars using your model, compare it to the measured data, and then you tweak the unknown parameters in your model until the simulated CC dollar perfectly matches the experimental one. They showed this worked beautifully. They used the measured C data from a 34-qubit system to precisely determine an unknown phase parameter that was deliberately hidden in the circuit. The optimization process correctly found the hidden value.
That's powerful. being able to accurately pinpoint microscopic details of a quantum system. I can see how that would be useful.
Absolutely. It opens doors. For instance, they suggest this technique could be readily applied in fields like solid-state nuclear magnetic resonance, or NMR.
NMR, like in chemistry labs.
Yes. This could allow scientists to get much more accurate estimates of things like dipolar couplings, the interaction strength between specific pairs of atoms or spins within a complex material. It's like getting a much sharper lens to see how materials work at the quantum level.
Okay, let's try to sum this up. There's a lot here. Takeaway number one seems to be quantum echoes are powerful.
Right. Standard measurements die out fast in quantum chaos, but these time reversal OTOCs hang on much longer, preserving sensitivity. They decay algebraically, not exponentially.
Takeaway two, it's the type of interference that matters most.
Definitely. The real magic, the key to unlocking extreme sensitivity and classical difficulty, comes from that large loop constructive interference that only the higher order OTOC, CC of S, can effectively see.
And takeaway three, we might actually be seeing practical quantum advantage emerge.
It looks that way, at least for this class of problem. Measuring 65 crime qubits took hours, while simulating it classically would take years on a top supercomputer. That makes OTOC2 a really strong candidate for demonstrating quantum computations that are both useful and genuinely beyond classical capabilities.
Okay, one final thought then. You mentioned earlier that OTOCs and this whole idea of information scrambling often come up when physicists talk about black holes.
That's right. The way information seems to spread and hide in chaotic quantum systems has parallels to theoretical ideas about what happens to information that falls into a black hole.
So, if understanding these quantum echoes, this time reversal and interference, is key to pulling information back from chaos here.
Well, it makes you wonder, doesn't it? Could these same principles harnessing interference across complex, time-reversed paths offer clues about the deeper mysteries of information? Maybe even how it might be retrieved or how it behaves near the event horizon of a black hole itself. It's a pretty mind-bending connection to think about.